So, hello everyone. I request you all to mute your microphones so that there is no noise from your side. I think that one of you has not done not done the same. So, Mr. Bhattacharya, can you please mute your microphone? Okay, I guess I will do it myself. So, as you all know that some microphone doesn't. Okay, it's fine. So, as you all know, that this course is being taught by Professor Sanjeev Sambadan, and there will be three TAs for this course who will be solving the problems for you, and you will get insights about the problems that will be in your assignments. So, these problems will revolve around the assignment problems mostly, so that you get an idea how you are going to solve the problems for your assignments. They will not be the same, uh, and if you have any doubts regarding regarding the assignment questions itself, although we cannot help before the assignments are submitted regarding the questions which are in assignment, mm, we can still try to figure out how we can help if you reach to us by our emails. For example, if anyone is having a doubt in a question, let's say in assignment 1, and its deadline is, let's say, 10th of the August, so we will just try to provide hints about that question, not solve that question fully. So you must drop a mail to any one of the TAs. There will be three TAs for the course. If you feel any doubt about any problem, you just drop a mail and say that we want a little bit of hint about this problem, and the TAs will try to provide only that much amount of hint which they feel will be sufficient for you to solve the problem. So that's one thing about this live session, that we will not be solving the problems which are going to be in the assignments. Although when the assignment due date is over, we can solve those problems. But a priori, we will not solve any problem regarding to the assignment which you will be provided. We will just try to revolve around those problems which you have been given. So as you will be all aware, you can see I have my email address over here. Likewise, all other TAs will also have their email address, and you are welcome to ask any question to the TAs regarding the coursework at any time. So you can contact me on my email if you have any queries, so that I can respond to your query at my earliest. So I am a PhD student at Department of Electrical Engineering, IIT Kanpur, and I will be one of the TAs, and there will be two more TAs. So let's get straight to the problem solving session. As you must have, I guess all of you must have gone through the lectures that professor has put on the platform, and I feel that you all must be aware of the quantum mechanics by now. So I am admitting all the students who are trying to attend the class. Until now, I guess 13 to 14 students have joined. So I guess it's good to go. So let's begin our problem solving session with the problems about quantum mechanics. So let's put this to start. Okay. So I'm admitting all whosoever is joining. So it's fine. I guess most of the people have joined. So I have given all the instructions. So let me repeat once more that this is my email address, and if you have any queries regarding the assignment problems, you can drop an email, so that I will try to provide hints only, not fully solve the assignments. We will try to solve the assignment fully only after its deadline is over. We will just, in this, for example, this is the first session. In this session, we will just try to solve the problems which revolve around the quantum mechanics, and which will help you to gain insights into the assignment problems and even much broader aspects that are related to the quantum mechanics. So let's get going, and let's start with our first problem. And I guess all of you must be seeing my another screen, which is saying that we have solved the question number one, where in this question number one we will be having two wave functions. I am not going into the theory because I know you all must have gone through the lectures. So let's get going with the problems itself. So this, as you can see over here, we have been given two wave functions which are physically realizable. It has been given to us. Now we have been told to show that the linear combination of these physically realizable states is also physically realizable. So basically what we are doing, we are just trying to use the superposition or the sum of the two states. Okay, so you must have heard professor saying that we can say that the psi is represented by plane wave solution. When he derived the operators, he said once that we can take the solution to be of the form of e to the power of iota. So when he took it in the form of the e to the power of iota, it was plane wave solution. Okay, so these psi's can be plane wave solutions. It can be of the form of e to the power of iota. And when you see the quantum solvers, like for example, whenever you solve the quantum equations, like for the quantum mechanics in the simulation world or in the real world for the new materials, let's say you are trying to solve the Schrodinger equation for the, let's say, silicon. So how you are going to assume the solutions for those psi's? Those psi's are mostly taken to be as plane wave solutions. Okay, we just take the linear combination with some factors attached to it. That will be the solution to the wave functions what we are going to obtain for any material. So the plane wave solutions, which are really important to us while solving any material. So likewise, as professor said, we can assume the solution of the psi to be of the form of plane wave, that is e to the power of iota something. So let's get going with that insight itself. Let's say that this we have this psi1. Sorry, I guess there is some problem with it. Okay, so we have been given that this psi1 of x comma t is physically realizable, and psi2 of x comma t, it is also physically realizable. What do we mean by the physically realizable? as you must all have gone through the lecture where professor told us how this psi, which we use to model a material, it is a modeling parameter to us. So what we do is we try to govern, or we try to impart some restrictions to this psi. We say this psi has to be continuous. That's one of the properties. It has to be bounded. Okay. So there are some conditions that are put on this psi values. So continuing with those properties which professor told us in the lecture, we are going to move and say that this psi between the limits minus infinity to infinity, let's say this psi1 is of the form of, let's say this psi1 is a times some psi1 of x comma t. Okay, so if we take its probability density, so it will simply be a square, that's the probability of finding this particle in the whole space. We are taking it to be one dimensional, let's be aware of that thing. So this will be simply psi1 square dx. It will be less than infinity. Okay, it will be not infinity. That's what we mean by the physically realizable system. It has to be bounded, it has to be present somewhere. Similarly, we will be having for this psi2 b square psi2 x comma t dx. It has also to be less than infinity, it has to be bounded. Now what we are going to do is we are going to use the linear combination of these two states. So what do we mean by the linear combination? Linear combination simply means it is a times psi1 x t plus b times psi2 of x comma t. That's what I was saying, that the solution to any, for example, any material can be a linear combination of the wave functions. It will be many wave functions. So it is similar to that. We are just going to see whether it is physically realizable, that we are going to see in the future slides. So this is the linear combination. We have to look at its probability. So we have to take its conjugate and we have to integrate it over the whole space in one dimensional. So it is psi star a times psi1 x comma t plus b times psi2 x comma t dx. Okay, so this is what it looks like, the linear combination and then its probability over the whole space. So if we try to, what I can say, if we try to break this, it will look like this. It will look like that we have minus infinity to infinity a times psi star x comma t plus b times, this is psi1, I guess this is psi2 x comma t. This has to be multiplied with, okay, this has to be multiplied with the a times psi1 x comma t plus b times psi2 x comma t, and this is integrated over the whole space in x. So it will simply be a square psi1 star x comma t into psi1 x comma t plus ab psi1 star x comma t psi2 x comma t. So this will be minus infinity to infinity, and plus it will be a into b psi2 star x comma t psi1 x comma t plus b square psi2 star x comma t into psi2 x comma t dx. As you must be all aware, what we said in the previous slide is that this psi1 star into psi and this psi2 star into psi, these are bounded. That's what we began with. Now we have to look at these two terms only. So what do these two terms give us? Since these two which are present over here, they are bounded because this psi2 star into psi is simply the psi2 mod square. So if we use this for these two, which I will encircle in red, we will use this Cauchy-Schwarz inequality. So this Cauchy-Schwarz inequality, it just says that if psi1 of xt and psi2 of xt are square integrable, that's what we saw. If they are square integrable, then their inner product is guaranteed to exist. Okay, so I just wanted to state it over here. We do not need to derive this Cauchy-Schwarz inequality. So if I use this inequality is simply that if I have, let's say, a function of psi between the limits a to b, psi1 of x and psi2 of x dx, it will simply be less than, the quantity which is psi1 of x square psi2 of x square. It is square integrable, so it has to be a and b, and there has to be dx over here as well. So this is what this inequality tells us. So from this we can clearly see this psi1 and psi2, since this inequality says that this value, this psi1 star into psi2 dx is less than the square integrables of the same functions. So it clearly means that this quantity will be less than infinity, and this quantity, which is the other quantity psi2 star into psi1, this will also be less than infinity. So what we will be getting is, we will simply be getting this minus infinity to infinity psi1 star of xt into psi2 of x comma t dx to be less than infinity, and similarly psi2 star x comma t into psi1 of x comma t dx to be less than infinity. So what we have seen that if we take the linear combination of two wave functions which are physically realizable, then the linear combination is also physically realizable. The linear combination, so these are important results. You just need to see how if a physically realizable state is present and another physically realizable state is present, then their combination will also be the physically realizable state. This will be really important when you solve the Schrodinger equation for a material which is new to you, because the solution, a complete solution, will be a linear combination of many wave functions, plane waves. Okay, it will be solution of, let's say, 10 plane waves. Psi1 will be of the form of a times some exponential of iota something, and some psi2 will be b times exponential of something. So it will be a solution of a plane wave solution, which will be a linear combination of these existing physically realizable single wave functions. So moving to our next problem, what we have seen till now is that how this wave function is physically realizable if we take a linear combination of any two physically realizable wave functions. Now, this is also another important factor which says that you must have seen the position operator. Position operator is nothing but it is simply x, sorry, in 1D it is simply x hat. This is the position operator. Professor told you about the momentum operator, etc. Let's not get into that uh, because you have already seen those in lecture. So the expectation value is nothing but if this psi is a wave function, the expectation value of x, it has been said in this problem. Let's first discuss the problem itself. It says that let psi be any wave function whose expected position is given by this delta x, sorry, this x in the braces. So as you have already seen in the lectures that there is some uncertainty associated with the position, because whenever we try to measure the position, there will be accurately the position, there will be some uncertainty associated with the momentum. As professor taught us in the lecture, he told how the wave, if we are having he gave a nice example that how a continuous wave will have a frequency associated with it, while as a wave which is just, for example, we have a rope and we just move it up and down once, and that in that case we will say that the wave is localized at a one position, but its frequency, it is not localized, it's unlocalized, it is present over the whole space for a localized wave. So similar is the case if we are going to measure the position in the quantum mechanical world, it will be expected position, okay, it will be probable position, okay, it will not be the exact position that we will be getting. As you have seen the Heisenberg's uncertainty principle, which professor taught us in the lectures, he told how there is uncertainty associated with the momentum and the position measurement. There will be some error associated with it. So this problem also says that we have this expected position. So as we know, what is the derivative of the position with respect to time will give us the velocity. So what we get here is the expected velocity, and the problem says please try to find this expected velocity. Okay, so we are going to find this expected velocity for a wave function which is of the form of simply psi. This can be any wave function. Let's say it is a plane wave function. Okay, so if this is the expected position, so we have to use the operators. So it will be simply psi of xt operating, and then this will be our psi. Okay, this is what the expectation looks like of the position. Okay, now we have been told to find the derivative of this expectation, okay, of the position. So it simply means we have to do the d by dt. Okay, wait a second. Okay, so this is the d by dt of, sorry, minus infinity to infinity psi of x comma t. Okay, what is happening with this? I'm sorry for this. Psi of xt, psi of xt dx. Okay, so this is what the derivative of this expectation will look like. So this is simply equal to, taking the x out, as we know, this is simply minus infinity to infinity, taking the x out as it's independent of time. So it will simply be, let's say it will simply be psi star d psi, sorry, d psi by dt x comma t psi of x comma t, okay, plus psi star, okay, x comma t d by dt of psi of x comma t. This has to be integrated with respect to x. So this has to be integrated with respect to x. Okay, so this is what we got, d psi by dt times psi of t plus psi star into d psi by dt. Okay, it's fine. So this is simply what we got from the UV rule. Okay, now what we have is, we simply have this, sorry, did I took this x out of integral? Oh, this is a mistake. It has to be inside the integral because dx is operating on it. It has to be integrated over the whole space. Okay, so it is simply x times this whole thing integrated with respect to the x variable. Okay, dx. So if we use the Schrodinger equation, if we use the Schrodinger's equation, Schrodinger's equation, as you have seen it in the lecture, it is simply, this is the energy part, this is the kinetic energy part, minus h square by 2m d square psi by dx plus v psi. This is the potential energy part. The Schrodinger equation is nothing but energy balance equation. Okay, it is simply the energy balance equation. So this d psi by dt is simply, if I take divided by iota h, it will be simply h bar iota. Okay, let me be careful while solving this, plus, okay, if I take the iota above, it should be minus. Okay, minus by h bar, okay, v psi. Yes, I guess it's right, it's correct. Okay, so this is what d psi by dt will look like if I solve the Schrodinger equation. Now if I take its conjugate, let's write step by step, taking conjugate of equation 1. Okay, so if I take the conjugate of equation 1, it will simply be d psi star by dt. This will be minus h bar, okay, sorry, I forgot to write d square psi by dx. Okay, so it will be minus h bar iota. Okay, iota conjugate is simply minus iota. Okay, 2m. Rest mass or any mass, for example, it is a real quantity. H bar is a real quantity, so conjugating it with won't affect. Okay, so it is h bar iota by 2m. So d square psi star. Now this psi, d square psi by d psi star, because we have taken the conjugate of it. So it will become plus iota by h bar. Potential is a real quantity, so v times psi star. So this is our equation second. Now what we can do with this equation is, we can put this equation back where, here, for this part only. Let me put it in red. For this part only, we now know what is d psi by dt in terms of d square psi by dx. Okay, so d psi of x comma t into d psi star by dt is simply, if we do it like this, now we have d psi by dt with us, we have d psi star by dt with us, so we can simply say this psi times d psi star by dt plus psi star d psi by dt is simply equal to, let's go back to the slide, it is h bar, this thing, this is our d psi by dt, so it is minus h bar iota by 2m, so it is minus h bar iota by 2m psi times d square psi by dx square. Okay, d square psi times dx square, this has to be in the brackets. Okay, plus iota times by h bar v times, I guess it was psi star into psi plus psi star times psi star times psi star times, okay, this thing, which is h bar iota by 2m, h bar iota by 2m into d square psi by dx square. This has to be dx star, okay. This will be, I guess it will be minus iota v times h bar psi star into psi. From this, you can clearly see that this quantity and this quantity will cancel out, okay. It is simply iota v by h bar psi star into psi. These two quantities will cancel out and we will be left with, let us take this h bar iota by 2m as common. We will be left with psi star d square psi by dx square minus psi times this thing d square psi x star by dx square. So this is what this psi times d psi star by dt plus d psi star into d psi by dt looks like. So let us put it as equation 3 because we will be requiring it in the upcoming slides. Now from this, we now need to obtain the dx by dt, which was our initial problem. How we can obtain it? We can simply say, we simply use this equation, d by dx of psi star d psi by dx minus times, so I am just trying to backtrack the whole thing, d psi star by dx. What will it be what will it be looking like to us? So it will simply be d by dx of psi star into d psi by dx, okay, this is one thing, plus psi star into d square psi by dx square. Actually I have to plus it over here, okay, I have to add it over here, so it will simply be, okay, it will be simply be minus times, it will be minus times d psi by dx into d psi star by dx, okay, minus times psi times d square psi by dx square. So from this d psi by dx into dx star by d psi star by dx and this d psi star by dx into d psi by dx, they both will cancel out, okay, this and this will cancel out and we will be simply left with, which is this term, we will simply be left with, that is this d by dx of psi star, okay, d psi by dx, okay, yes, minus psi times, sorry, it has not to be square over here, psi star by dx is simply equal to psi star d square psi by dx square minus psi times d square psi by dx square conjugate. Let's keep it as equation 4. So this is this psi star into d square psi by dx square, this term, if I compare with the equation 3, what we got, this thing over here, this is the thing what we got, sorry, this is the thing what we got, and this whole thing is equal to this thing. Okay, okay, this whole thing is equal to this thing. So what we can do is we can use this equation 4 using 3 and 4. Okay, if we use this equation 3 and 4, we will simply get this dx by dt to be equal to, this had h bar iota by 2m outside, h bar iota by 2m outside, minus infinity to infinity. Okay, so this whole thing, where is it, this whole thing, this in red, which is in red, this whole thing has to be replaced by this thing only. Okay, and what we had outside was this x. Okay, this x multiplied by d by dx, okay, of this psi star. Okay, this is d by dx of psi star, d psi by dx. So what have we done? We have done one important what you can say transformation over here. We have transformed our equation, which was in time domain only, and time domain plus the space domain, we have transformed it to the space domain only, which is x as a variable. So this is minus psi d psi star by dx. This whole was integrated with respect to dx, as far as I remember. Yes, this whole thing has been integrated with respect to x. Okay, so this is the dx. So if I now solve for this, it should be rather easier as compared to the previous equation. Sorry, what has happened with this? Okay, sorry, it has closed. Okay, so it is simply now an equation where we have to integrate by parts first. This dx and d by dx and dx will go, and we will simply be left with this thing, which is h bar iota by 2m minus infinity to infinity x. This has to be multiplied by with psi star. Okay, so we have to integrate it with respect to this dx. So it will simply be uh, d by dx. If we integrate it with respect to this thing, so it will be simply this psi star by dx minus psi d psi star by dx. Okay, so this has to be between the limits. Okay, this is multiplied, this has to be between the limits of minus infinity to plus infinity, minus h bar iota by 2m. What we have done, you have used UV rule to integrate it. Okay, so it is simply h bar by 2m minus infinity to infinity. So we have to differentiate x now. Okay, using UV integration rule. Okay, so it will be simply this psi star d psi by dx minus d psi star by dx psi. Yes, this will be this has to be integrated with dx. We have used simply UV rule of integration. Okay, now what about this term, which I will quote in red? What about this term? Okay, what about this term? What does this indicate to us? It indicates that since the limits, okay, since the limits are between minus infinity to plus infinity, as we all know, at infinity this psi star has to vanish in order for it to be physically realizable. Similarly, this psi has to vanish at plus minus infinity. So what we can say, that we can say it like this: psi should tend to 0 when x tends to plus minus infinity. So it means that this whole quantity which we will be putting in this color, okay, this whole quantity will come out to be equal to 0. Okay, this whole quantity will come out to be equal to 0. And now what we will be left with, we will be left with this quantity only. Okay, this quantity only. So let's write it down again. So it is simply dx by dt is equal to minus h bar iota by 2m. Okay, it is minus infinity to plus infinity. Let's take this thing psi star d psi by dx into psi. So it is simply psi star d psi by dx minus times psi times d psi star by dx with respect to dx, integrating with respect to dx. Now we have still not solved our whole problem. We are still stuck. Where are we stuck? We now need to eliminate one of these two, because what we are required to find, it is somewhat of a form of psi star d psi by dx integrated with respect to x dx. Okay, so let us do it like this. It will be h bar iota by 2m. Let's keep the first term as it is, psi star d psi by dx, and let's do one thing. Let's use uv on the second thing. Okay, so it will become like this. It will be psi into psi star with limits minus infinity to infinity, plus this has to go. It will be simply minus infinity to infinity. We have to differentiate this d psi by dx times psi star dx. Okay, so as we know, uh, at this whole quantity has to go to 0 at x equal to plus minus infinity. So what we will be left with is this quantity, which is minus h bar by 2m d psi by dx into psi star dx. Okay, so these are, if we add these two, it will simply be 2 times minus infinity to infinity psi star d psi by dx, sorry, d psi by, I don't know what is happening with this today, d psi by dx dx. Okay, this 2 and 2 will go, and we will be simply left with minus h bar iota by 2m minus infinity to infinity psi star dou psi by dou x dx. Okay, this is what we were required to find. So this was our result. So this is the result we obtained, which is given over here, So the expectation of this, the derivative of the expectation, which is the velocity, is simply equal to minus h bar iota by m integral psi star dou psi by dou x dx. So this is what we arrived at the end. So if anyone has any question till now, he can ask. I will try to answer that question regarding these problems, these two problems which we have solved. Let me check the chat meanwhile as well. Okay. So I assume we will have to move forward. Okay. Okay. Let's move forward. No problem. If you have no questions, so let's move to the third problem. You have gone through the, I guess, this infinite potential well, which was in the first week. where the professor just showed us how a particle which is trapped between two infinitely high energy potential wells, if it is bound in that well, how its solution will look like. He told us that its solution is of the form of sine x, some sine kx, let's say. And then we solved for its k, which is the wave number, and we solved for its normalization constant, and we obtained the solution of the form of the solution for this infinite potential well, this solution for this infinite potential well, psi n. Psi n was simply this root 2 by L, where the L was the length of the box, and this is the normalization constant, sine n pi, okay, by L x. This was the solution. You must have seen it in the infinite potential well lecture taught by the professor to us. So in this problem, what we have been told that we have to check the solutions of the Schrodinger equation to the infinite potential well problem. To the infinite potential well problem are orthonormal. Okay. So for orthonormality, we know that we have to check for the solutions to be orthogonal, and as well as the magnitude, the inner product of these two has to be equal to 1. Okay, that is the condition for the orthonormality. So if psi n is the nth solution of this infinite potential well problem, as you have seen that there will be many solutions depending on the value of n. The professor told us, for example, when n is 1, it will look like a sine curve, and with zero nodes touching in the middle. And when it will be having n equal to 2, we will be having a sine curve with a node intersecting the zero axis in the middle. Similarly, we will be having solutions for this sine of, let's say, 3n, 4n, 5n, and we can have many solutions for this infinite potential well. And this sine n is the nth solution, and this sine m, let us say, this is the mth solution. Okay, m pi by m. So what we have to show is, we have to show that these solutions are orthonormal. This psi n and psi m, which are the solutions of this infinite potential well problem, they are orthonormal to itself. Okay, so what we will do is we will look at its inner product. So let's look at its inner product. So it is, the limits will be 0 to L. Okay, because we are confining our solution to the well, potential well, which is of the length of L. It is not between the minus infinity to plus infinity. The solution of the Schrodinger equation is bounded between these limits 0 to L. It has to vanish, the wave function has to vanish at x equal to 0, and a wave function has to vanish at x equal to L. So it means the wave function will exist only between the limits of 0 to L. So this is sine m conjugate x into sine n of x. There is no fun in doing the conjugate because this is a real solution. So let me write down, this is the inner product. Okay, inner product. Be careful while you are checking for the conditions on a solution. As you know, this solution has to be continuous, and its derivative, the wave function derivative, it has also to be continuous. Okay, these are the main conditions while looking for any general solution for any system you are going to solve. So this is the inner product. So it will simply be equal to 0 to L root of 2 by L sine of m pi by L x into, since this is a real solution, 2 by L sine of n pi by L dx. Okay, so let's say this is the integral, this is the inner product. Okay, now if we solve for this I, it is simply equal to 2 by L 0 to L sine of, what was it, m pi by L x into sine of n pi by L x dx. Okay, now let's get into mathematical aspect. We know sine of A into sine of B is simply cos of A minus B minus times cos of A plus B by, okay, let's use this formula and try to solve for it. It will be 0 to L, okay, cos of, let us take pi by L to be common, m minus n, okay, m minus n times x, okay, yes, this is cos of A minus B. Cos of A plus B will simply be cos of pi by L m plus n x, okay, yes, so this whole has to be integrated with dx and has to be divided by 2. So this 2 and 2 should go, okay, this 2 and 2 will go and we will be left with 1 by L, okay, this is simply 0 to L cos of m minus n pi by L x, okay, minus times cos of m plus n pi by L x times, this is whole integrated with respect to dx. Okay, now from this we need to infer for the solution. So it is simply 1 by L, we have to integrate it, so it is L by pi m minus n, okay, sine of m minus n pi by L x with limits 0 to n. Similarly, for this m plus n thing, it will be minus 1 by L, okay, minus 1 by L. This will be L by pi times m plus n, okay, m plus n sine of m plus n pi by L x with limits between 0 to L. I guess it is congested over here. Let me write it in the another slide. Okay, let me write it in another slide. Insert new slide. So it will be simply 1 by L, L by pi, L by pi. It was m minus n. Okay, sine of yes, m minus n pi by L x with limits 0 to L. Similarly, it was minus L by pi m plus n sine of m plus n pi by L x between the limits of 0 to L. Okay, so it is what it looks like. Okay, now the solution will simply be 1 by L will go with this L, okay, So we will be left with 1 by pi m minus n. Okay, putting the limits, it will be sine of m minus n pi. Okay, L and L will go, and sine of 0 is 0. Okay, simply. So this is minus 1 by pi m plus n sine of, okay, this is sine of m plus n pi. Okay, let me check the correctness. I guess it's correct. Okay, yes, it's correct. So now we know this m and n, they both are integers. That's what the condition was on the solution of the infinite potential well. This n and m are integers, that is, it has to be 1, 2, 3, 4, like that. So if m and n are integers, then m plus n, for example, let's say if m is not equal to n, okay, let me put it like this. If m is not equal to n, okay, then we know that, for example, m is 4, let's say, and n is, let's say, 2. So it will mean m minus n is 2 and m plus n is 6. And sine of 2 pi is 0, sine of 6 pi is 0. So it means that when m is not equal to n, this whole solution, this is coming out to be equal to orthogonal solutions. Okay, this is coming out to be the orthogonal solutions. Now if m is equal to n, that's where the main condition arises. Okay, if m is equal to n, you can clearly see if m is equal to n, it will simply be equal to sine of, let me write it in red, if m equal to n, it will sine of m plus n will simply be equal to, let's say, 2n. Okay, it will be simply equal to sine of 2n, and sine of, sine of 2n pi is equal to 0. So this term will be equal to 0. Now this term, this is where the main problem will arise now. Okay, so what we have to do, we have to say this term, which is 1 by pi m minus n sine of n minus m pi, sorry, m minus n pi, I use m minus n pi. So if m is equal to n, this is 0, this is also 0. It is 0 by 0 form. So we have to resort to the L'Hopital's rule in order to find the whether the solutions agree for the condition of orthonormality or not. So let us put m minus n to be equal to y. Okay, so we will be simply left with 1 by pi, okay, sine of y pi by y. So this is for m equal to n. Okay, let us be clear about this thing. So it is simply, if I take the L'Hopital's rule, which will be limit y tending to 0, 1 by pi sine of y pi will simply be pi times cos of y pi by 1. Okay, so this is limit t tending to 0, and as a result of this thing, this and this will go, and this whole thing, this I will come out to be equal to 1 if m is equal to n. Okay, so what does it tell us? It tells us this whenever m is not equal to n, we are getting this integral to be equal to 0, and whenever we are having this m equal to n, we are getting this to be equal to 1. So it clearly says that the solutions are orthonormal. Okay, simply uh, the psi of n and psi of m was orthogonal to each other, which when we saw m is not equal to n. That was one of the important conclusion that we got from this problem about this psi solutions. Okay, now let's move to another problem, which says that uh, we have to, as you have seen that in the Heisenberg's uncertainty principle, which professor taught us, he told that we cannot measure the momentum and the position to what we can say to have zero accuracy, can say zero accuracy error. There will be some error associated with it, which was given by h bar by 2 pi. Okay, so if we are trying to measure the position, then we will have to associate some error with it if we want to try to measure the momentum, because simultaneously we cannot measure the both, and that's what Heisenberg's uncertainty principle was all about. Now this what this commutator, uh, this is some operator kind of a thing, and this commutator, this also tells us the same. What does it tell us? It tells us that if we can measure the two observable quantities at same time. Okay, that's what it tells us. So this commutator can be seen as one kind of a what you can say, one kind of a Heisenberg's uncertainty principle checker. Okay, if we want to check the Heisenberg's uncertainty in the measurements of position and the momentum, we need to check this thing. Okay, so this is simply, this commutator is simply, this operator is like this. If it is a commutator of a or b, is simply ab minus ba. Okay, if there is no difference, then we can measure both the quantities with at the same time. But if there is some number associated with this commutator, we can say that both the quantities are not measurable at the same time, and we will be requiring the Heisenberg's uncertainty principle measurements to get insights about the errors which will be associated with the position and momentum measurements. So it's that simple, this commutator operator. Now let us operate this on this x comma p on some psi, which is some wave function which we want to measure on. So as we know, this x is the position operator, it is simply x hat, and this p is the momentum operator, this is p hat, operating on psi, which is some function of x. Okay, similarly, this is p hat, this is what commutator operator looks like, ab minus ba. Okay, this is what we have done, ab minus ba. Now a is the position operator, x hat, operating on this our wave function. Okay, now we know the x hat, which is a position operator in one dimension, it will be simply x, and this momentum operator is h bar by iota, tau by tau x, which will be operating on this side, and this will be simply h bar by iota tau by tau x of x. Okay, times psi of x. This is the whole thing which has to be operated on. Okay, now from this, what we can say, that we write it clearly, this p is simply h bar by iota tau by tau x. That's what we have used, and simply x hat is equal to x. This is as simple as it gets. Okay, now if we now say this thing, let's keep the first term as it is, which is x h bar iota. Okay, tau by tau x of psi x minus times, it was minus times h bar iota. So what we are using, we are simply using a UV rule. Okay, you are simply using UV rule. It will be minus h bar iota. It was psi of x dou x by dou x minus times. Okay, so it is minus times h by iota, h bar by iota. Okay, into x dou psi x by dou x. Let's check the correctness. UV rule, it will be first dx times psi. Okay, then it will be dou psi x by dou x into x. That's what we have done over here. So from this, this term and this term looks similar. It is dou by dou x, x, h bar by iota, dou by dou x, h bar by iota, x. Okay, so this term and this term will go, and we will be simply left with minus h bar iota by psi of x. So this is x comma p operating on x psi of x, or simply this is minus h bar by iota, or simply h bar iota. So what we have found is this commutator operator has, we cannot measure this x and p because this commutator operator has some value which is h bar iota associated with it. Okay, so we cannot measure these two quantities at the same time. Now let's move towards another problem which you must find a bit easier as compared to the previous problems due to the familiarity or the same what you can say, the same kind of questions that we solve in our uh, coursework which professor teaches us, and he has also taught us how we can normalize the wave function and find the value of the constants. So this problem is somewhat associated to that kind of a thing where we have to find the expectation value of x, and we have to also find the normalization constant. So uh, if now I go for this problem first. Okay, so let us go for this problem. Sorry, let's go for this problem. So it says that psi of x is equal to ax by a. Okay, ax by a between the limits 0 to, and it is equal to, a times b minus x by b minus a, and it is 0 for rest. So this is a simple problem as compared to the previous problem. So we have to solve for it between the limits of 0 to a and then between a to b. This is as simple as it gets. So it would simply be, if we are going for this normalization, simply we have to integrate it over the whole space. We have to find its probability density. So it is, this has to be equal to 1. That is the probability of finding this particle in the whole space. is this has to be 1. So between 0 to a, okay, between 0 to a, it is ax by a, okay. So it is between 0 to a, it is ax by a. Its conjugate will simply be ax by a because it's a real quantity, dx, okay, plus the limit was a to b, okay, a to b, and it is a times b minus x by b minus a, a times b minus x by b minus a times b minus x by b minus a dx. This has to be equal to 1, okay. So it will simply be capital A square by A square x square dx 0 to a plus a to b a square, sorry, let us put this outside the integral as well, a to b minus a whole square, this is b minus x whole square dx, this has to be equal to 1, okay. So it is simply a square by a square x square. If we integrate it, it will be x cubed by 3. It will limits 0 to a, plus this will be simply a square b minus a square. Sorry again for this. Where were we? Okay, it has somehow got, okay, let us do it again. It is a square by a square x cubed by 3 0 to a plus a square by b minus a whole square, okay. This will be minus 1 b minus x cube by 3. Am I correct? Yes. Between the limits a to b, this has to be equal to 1. Yes. So this will be simply a square by a square into a cube by 3, because 0, when we put it 0, it will be 0. This will be simply a square minus 1 b minus a whole square, b minus b will be 0, okay, b minus b cube, minus times minus 1 a square, okay, b minus a whole square into b minus a whole cube equal to 1, okay. That's what it looks like, okay. So this thing will be equal to 0, and this 3 will go with this thing, this whole thing will go with this, and we will be left with simply, we will be left with a square by 3, a square by 3 plus square by 3 plus, it uh, is a square b minus a, okay. Square b minus a by 3. Where did this 3 go? Here you have a 3 as well. Yes, it has 3 associated with it. So it is simply plus a square minus a. I guess it's correct now. It is. It had some. Oh, sorry. Undo. So it had some a associated with it as well. So it is a. It is a square. A square by 3 plus a square b minus a square 3 equal to 1. Okay, this a square will go, and we will be having a square b equal to 3, or we will be having this a equal to root of 3 by b. So this is the value of the normalization constant. for this problem. It comes out to be equal to root of 3 by b. Okay, let me have some water. So this we have been able to find. We have found the normalization constant value a. Now we have to find the expectation value. Okay, expectation value. We did a more rigorous problem about the expectation previously, which was, where was it? I guess it was the second problem. Yes, here it was, the expectation value of the position x. So we have to follow the similar steps. So can anyone help me with this? If anyone is willing to help me with this, he or she can unmute and help me with solving the expectation value of this problem. What should I write? What should I begin with? I have shown you how to write down the expectation of the position. So I need to find the expectation of x. So how should I go about this problem? If anyone among you is willing, they can unmute and speak about this. If you are willing, okay. I'm not saying that you have to solve the whole problem. Just give me the hint what I should do to solve for the expectation of this problem. Okay, no problem. So let me myself solve it, and you guys understand it again rigorously. So it will be mostly the mathematical part. You just had to say that we will just use this expression what we used in the question 2 in today's problem, in today's session, which was the question 2. So if the expectation was simply, let me write it down again, the expectation expectation of x is simply equal to minus infinity to infinity, okay, psi star x, x psi of x dx. So that's what you were required to say. Okay, it's as simple as that. Okay, now it's now same mathematical problem that we are going to solve. Okay, so what was it? The expectation of x. We have to solve the same mathematical problem. So this quantum mechanics is more of a, what we can say, these problems are more associated with the mathematical aspect. You must have seen that there are problems in the assignment. We say whether this function is continuous, whether this wave function is physically realizable. So what does it mean? We have to check its mathematical existence. Okay, so this expectation over here, 0 to a, I guess it was ax by a, ax by a, ax by a, x times ax by a dx plus a to b. A to b we had, okay, we had a by b minus a, b minus x. So it is a times, it's a times b minus x, b minus a times x into a times b minus x, okay, divided by b minus a dx. So it's now the same mathematical problem we are going to solve for. So it will be simply will be simply a square by a square. It will be x cube 0 to a x cube dx plus a square b minus a whole square ab b minus x square x dx. Here, so it is simply a square by a square. Okay, this will be x to the power 4. Second, x to the power 4 4 0 to a plus a square b minus a whole square. So now we have to use the UV rule over here. So it will be simply minus times b minus x cube 3 into x minus plus. So it will be plus times. This will be having limit a to b. This will be a to b, b minus x cube by 3 dx. Okay, this will be whole multiplied with this thing. Okay, so it will be simply a square a square. Okay, it will be simply this thing will be a square by a square. This will be a to the power 4 by 4. So this will go to 2. This will go. It will be a square by 4. So let me write it down simply to be equal to a square by 4 plus, okay, it was a square by b minus a whole square. B minus a whole square. Okay, this thing was multiplied with b minus of b, it is b minus a into a, b minus a into a. Okay, it is b minus a cube by 3 into a, and this had to be integrated plus b minus x to the power 4. So it is minus times b minus x cube. So it is minus times b minus x to the power 4 by 12 with limits 0 to a. Okay, so it is simply, sorry, is simply a square by 4 plus a square b minus a whole square. Okay, so it will be b, I guess it was a to b, sorry, it was a to b, it is between a to b. Okay, so it is plus, it is b minus a cube by 3 into a plus b minus a to the power 4 by 2. Okay, so let us take a square by 4 plus a square b minus a square, this b minus a cube by 3 to be common. This will be a plus b minus a by 4. Okay, so it will be simply, this will go, this will be a square by 4 plus a square b minus a by 3, 4a minus 3 minus a will be 3a plus b by 4. Okay, so this is what it will look like. So now if I take this a square to be common, if I take this a square by 4 to be common, okay, this a square by 4 to be common, it will simply be a square b minus a, b plus b minus a into 3a plus b by 3. So it will be 3a square by 12 plus 3ab, sorry, sorry, it is 3ab plus b square minus 3a square minus ab. Okay, so 3a square will go with this. Okay, and this will be 3ab, this will be 2ab plus b square. Okay, 2ab plus b square into a square by 12. This is the expectation value. Now the value of a came out to be equal to 3 by b, root of 3 by b. Sorry, it came out to be equal to root of 3 by b. So we have to put it over here. A square will be now, sorry, 3 by b, 3 by b into 12, taking b common from this, 2a plus b, b and b will go, will be 4, it will be 2a plus b by 4. So this is the value of the expectation of x. Okay, this is the value of the expectation of x, 2a plus b by 4. So what we have done, we have found out the normalization constant and the expectation value as well. Now let's move towards another problem. It says that uh, we have to look at the Schrodinger equation. Wait a second. Okay, let us keep this. Okay, so we have to solve for the probability of finding a particle between the limits. The solution is given. The Schrodinger equation solution is given, which is root of 2 by a naught exponential of minus x by a. So we have to determine the probability of finding the particle between some limits, which is for a it is 0 to a naught by 4, for b it is a naught by 4 to a naught by 2, and for c it is a naught, between 0 to a naught. So what you can say, okay, so what we have to do, we have to find the probability. Now we have to look into probability 1. Let us say for a part we will be looking into probability 1. Probability 1 will simply be 0 to a naught by 4. Okay, psi is given to be equal to 2 by a naught exponential of minus x by a naught root by 2 a naught x and dx. Okay, so it will be simply 2 by a naught exponential of minus 2x by a naught dx, 0 to a naught by 4. So it is simply 2 by a naught minus a naught by 2 exponential of minus 2x by a naught, okay, with limits between 0 to a naught by 4. So it is simply this a naught and a naught will go, It will be simply minus times e to the power of minus 2 times a naught by 4 by a naught. Okay, this will go with this thing. This will be 2. This will be simply 2. This will be 1. Okay, it is simply minus of e to the power of minus 1 by 2 plus 1. So if we use the calculator, if we use the calculator, exponential of exponential of minus 0.5 is 0.6065. So it comes out to be equal to 0.3934. So this value comes out to be equal to 0.3934. So this is the probability of finding the particle with a wave solution, with a wave function solution given by root of 2 by a naught exponential of minus x by a naught between the limits 0 to a naught by 4. Okay, so now the another part of this thing is we have to find its solution between the limits a naught by 4 to a naught by 2. So it will simply be as slide. So it will simply be equal to what we did is minus 1 for part B. Sorry. Okay. So it is minus 1. Okay. Exponential of 2x by a naught between the limits of a naught by 4 to a naught by 2. So it will be simply minus times exponential of minus 2 times a naught by 2 times a plus exponential of minus 2 times a naught by 4 into a naught. Okay, it will be simply minus times exponential of minus 1 plus exponential of minus 1 by 2. So exponential of minus 1 by 2 we found out to be 0.605. Now exponential of minus 1 is 0.36. Okay, 0.367 minus it is 0.605. So it comes out to be equal to 0.23. 0.23. Okay. Now for the C part, it says that we have to find its probability between the limits 0 to a naught. 0 to a naught. So it is simply minus times exponential of minus 2 by x, sorry, 2x by a naught 0 to a naught. Okay, it will be simply minus times exponential of minus 2 a naught by a naught plus 1. Okay, this will be 1 minus e to the power of minus. Okay, e to the power of minus 2 is simply 0.135 minus 1. It comes out to be equal to 0.86. Sorry, 0.646. Okay, actually the battery is just slowing down. Okay, so we have found out it to be equal to 0.846. So now we have found out the probability, how to find the probability density. Now let's move to another problem. First of all, let me get the charger. Second. So, thank you for waiting. The charge of iPad. Okay, should work now. Second. Thank you. So now let's move to another problem, which says that an electron has a kinetic energy of 12 millielectron volts. So this electron has a kinetic energy of 12 millielectron volts, and we have to determine its de Broglie wavelength. Okay, so the kinetic energy is 12 electron volts. Okay, kinetic energy is simply given by P square by 2m, and m, the rest electron mass, is 9.11 into 10 to the power minus 31 kg. Okay, from this, momentum is simply equal to 2m ke. So momentum is simply equal to 2 times 9.11 into 10 to the power of minus 31 into, since we are dealing in SI units, 12 into 10 to the power minus 3, we have to multiply it with the electronic charge. We are dealing in the SI units. 1.6 into 10 to the power of minus 19. So this will be the value of E. So let's calculate it. Let's check what it comes out to be equal to. So it's 2 into 0.11 into 12. So it comes out to be equal to 5.91 into 10 to the power of minus 25. Sorry, 10 to the power of minus 26. 10 to the power of minus 26 kg meter second. So this is the value of the momentum. Now we know from this the momentum is given by h by lambda, or de Broglie wavelength is given by h by p, which is simply which is simply h has a value of 6.625 into 10 to the power of minus 34 divided by 5 point something, it came out to be 5.91 into 10 to the power of minus 26. So let's divide these two values. 6.625 1, it comes out to be equal to 1.12 to the power of 8 meter, or it is 112 angstroms. Okay, so this is the a part of that problem. Now the problem, now the part B of the same problem, it says that we have to find the momentum and kinetic energy when we are given the mass to be equal to 2.2 and de Broglie wavelength is 112 angstrom. So it is the same problem but with different quantities that need to be extracted. So M is 2.2 into 10 to the power of minus 30. Okay, and lambda was 112 angstrom. Okay, so now it means that momentum will simply be h by lambda, which is 6.625. Wait a second, 6.625 into 10 to the power of minus 34 divided by 112 into 10 to the power of minus 10, which simply comes out to be equal to, let's calculate it, 6.625 12 comes out to be equal to 5.91 into 10 to the power of minus 26. Okay, it is same as the previous problem. Okay, now the kinetic energy will be different because the mass is different. So we expect the kinetic energy to, to reduce a bit as compared to the previous solution. So it is p square by 2m because the effective mass has increased. It has increased from 1.6 to 2.2. So we expect the kinetic energy to get reduced. So it is simply 5.91 into 10 to the power of minus 26 whole square divided by 2. M is 2.2 into 10 to the power of minus 30. Okay, so let's solve this. Okay, let's solve this calculator. Let me solve this on the calculator. Okay, 5 it comes out to be equal to, kinetic energy comes out to be equal to 7.95 into 10 to the power of minus 21 joule. Now professor told us that we have to deal in the electron volt units. So for that we simply need to divide it by the electronic charge. So 1.6 into 10 to the power of minus 19. So it is simply 4 point something. Let me divide it accurately. Is 7.95 divided by 1.6, which is 4.96. 968 to be exact. 968 into 10 to the power of minus 2 electron volts. Okay, so this is what the a value of the energy came out to be from this expression after solving for the kinetic energy when the effective mass changed from 1.6 to 2.2 into 10 to the power of minus 31, which is almost the 1.4 times of the effective mass of the rest effective mass of electron. So I guess uh, that's it for today's problem solving session from my side. So if any one of you has any query or any question, they can type in the chat or they can unmute themselves and speak about the issues or the queries they are facing, or any suggestion they need to they want to provide. They are welcome for that as well. And also I want to remind you that there will be another session after this from 5 to 7. You are requested to join that session as well. So uh, I want some feedback from your side. If anyone is willing to give his feedback uh, about anything or any question, is welcome to ask. Please unmute or write in the chat, whatever you feel comfortable. Okay. So I guess we have. Okay. Actually, there is one Excel sheet that NPTEL course team will provide you. In there will be all the three TAs listed who will be solving the problem sessions, and I will be uploading it in my Google Drive, and the team will share with you the Excel sheet where the link of the Google Drive will be provided to you. So yes, you can take these notes from the Google Drive itself. I will provide these notes, and these video recordings, I guess they will also be uploaded uh, in the same Excel sheet. So there is no, what I can say, this is confirmation from my side that it's okay, that I will provide these things. Okay, so I guess if we have no questions, we can end this meeting so that you can rest for 10 to 15 minutes, and you can attend another session which will start from 5. So I request you all to attend that session as well, and I will take a leave. So I request you to leave the meeting if you do not have any question. If you have question, I am free to answer your question. So I guess we have to end this meeting. Thank you for joining the meeting. Thank you.